Citrini Research published a fictional memo from 2028 where AI had gutted white-collar jobs, tanked the S&P by more than 38%, and pushed unemployment past 10%. The Dow dropped 800 points the following day. Jack Dorsey cut 40% of Block's workforce that same week. His reasoning? Intelligence tools have changed what it means to build and run a company. No matter what your opinions were on that essay, it exposed something fascinating. Most people have no idea how the AI economy actually works. For the market to crash based on one blog post means that a lot of people with money and participating in this economy have not already formed strong opinions on AI and its impacts. They have played around with the tools and they can see a world where AI is contributing to the greatest economic boom or collapse, and they can be influenced by how articulate someone is on a podcast or eloquent they are in a blog. And yes, no one truly knows what will happen, and likely whatever does happen will be labeled a black swan event in some way. But there are raw inputs that I think can ground our predictions and understandings of this AI economy. This video will give you the mental map to the most important elements to AI value realization, and the key bottlenecks and trends to be aware of. There are 4 building blocks to AI, and if you are able to understand these 4, you'll be able to make much better sense of almost every AI headline and not be turned into a bull or a bear in a single day. For a quick intro, friends, my name is Cole. I studied philosophy and computer science at UCLA, where I also started the AI Robotics Ethics Society. And since graduating, I've been working at Boston Consulting Group, and I am soon to start another professional adventure that I'll discuss in a future video. Before we get into those 4 building blocks, this is a 75-second explanation of AI that should sharpen your intuition on what AI can and cannot do. A lot of people hear next word prediction when it comes to AI and large language models and think, okay, so when I ask it what's 2 plus 2, it's just seen 2 plus 2 equals 4 a million times on the internet, and it's predicting that 4 comes next. That's not really what's happening though. What's actually going on is that through training, the model has developed internal representations, patterns encoded across billions of parameters that approximate what addition is. It's not retrieving an answer. It's built something like an internal concept of addition that it can apply to novel problems, including ones it's never seen in its training data. That's how it can handle a calculation like 1847.2 plus 2391.89. It's not looking that up. It's applying a learned pattern. Now, that representation of what we deem similar to addition is not perfect. It's learned statistically, not by programmed rules, which is why these models can occasionally botch arithmetic that a $5 calculator handles without issue. But the point stands. The parameters don't store answers. They store capabilities. When I get into algorithms and data, some of what I just described might be helpful. Let's get into these 4 building blocks, starting at the bottom. Energy. Every AI model, every ChatGPT response, every image NanoBanana generates is run on physical hardware inside data centers that consume enormous amounts of electricity. To make the scale of energy required easy to understand, I'll describe the 2 methods of measurement. Gigawatts measures power, how much energy can be drawn at a singular moment. So if a data center needs 1 gigawatt, that is essentially saying that at a given moment, it will need that much electricity in the pipes. If you imagine data centers are like a car, this metric is like the miles per hour. Terawatt hours measures energy over time, how much electricity is actually consumed over the course of a year. And if data centers are that car, the terawatt hours could be analogous to the odometer's reading of the total mileage in the year. And to connect these 2 metrics, 1 gigawatt running continuously over the course of a year is equal to about 8.76 terawatt hours. So how much power does AI take? Enough that it's looking like it could be one of the most severe bottlenecks for AI value realization. The IEA expects the global data center energy requirements to more than double by 2030 to around 945 terawatt hours. That is slightly more than all of Japan's annual electricity consumption. The frontier of AI infrastructure is moving to AI data center campuses that require hundreds of megawatts to up to 1 gigawatt. If companies fail to secure that electricity, they may have the chips, the land, and the infrastructure, but not the capacity to turn it on fast enough. That is why the leading AI players are moving upstream into energy itself. Microsoft signed a 20-year deal restarting 3 Mile Island Unit 1 to bring back more than 800 megawatts of nuclear power. And Google partnered with Kairos to develop up to 500 megawatts of advanced nuclear power. These are meaningful moves, but not definitive solutions. The key players are trying to exhaust the solution space for energy, as it could be the ultimate constraint from capacity coming online. And yes, this even means considering space.
It will be by far the cheapest place to put AI will be space in 36 months or less.
Time for a quick, insightful side tangent on energy. Gavin Baker, a legendary tech investor who has been covering NVIDIA for over 20 years, said on the Invest Like the Best podcast that he believes that the most important development in the next 3 to 4 years will be data centers in space. Why? Well, from first principles, space solves every energy and cooling problem at once. The sun is 30% more intense in space, there's no atmosphere blocking it, and a satellite can stay in sunlight for 24 hours by proper positioning. And you can just radiate heat out from the dark side of the satellite. And with laser interconnects, communication through the spatial vacuum can actually be faster than fiber. And this looks like where xAI is headed with their energy investments. Though there is investment and excitement here, it is an extremely challenging engineering problem to put massive data centers in space, and cooling at data center scale in the vacuum of space is far from solved. Radiating heat works in principle, but doing it reliably across thousands of GPUs, generating enormous thermal loads, is a completely different challenge than cooling a satellite. In the next video, I will touch more on the different opportunities within the energy sector, but the two emerging companies worth keeping an eye on in this space are Oklo and Fervo. Oklo is trying to build flexible, more advanced, smaller nuclear reactors, while Fervo is trying to be a next-generation geothermal company. Their thesis is that they can provide 24/7 clean power through modern drilling and getting underground heat at scale. If this info has been helpful so far, you clicking that like or subscribe button genuinely means the world. I'm still just a monkey talking to a screen, trying to parse these educational topics, and it's an objectively odd thing to do. But any support makes it feel like broadcasting these deep dives is worth it. Thank you so much. Back to the video. Let's get into the second building block, compute. Okay, so the energy flows into data centers, but what is in those data centers? Chips. Specifically GPUs, or graphics processing units, that can run thousands of calculations simultaneously, which is required to run and train these large models. And the fascinating part about these chips is their supply chain. It has to be one of the most concentrated and fragile things in this economy. It essentially depends on 3 companies in 3 countries. The now household name NVIDIA, based in California, designs the chips. They have over 80% of market share for AI's GPUs. Their gross margins are above 70%, and they became the first $5 trillion company in 2025. TSMC, Taiwan's semiconductor manufacturing company, makes the chips. They fabricate 99% of the AI accelerator chips. 99%. Samsung is an oh-so-distant second. TSMC is what's called a foundry, a factory that makes chips designed by other companies. And it's really hard to overstate the moat they have. A single cutting-edge foundry costs $40 billion to build. That's 4 times the cost of a nuclear power plant. And the Taiwanese take extreme pride in this industry, from the manual laborers to the PhD level managers. And they have the institutional know-how that's been compounding for decades. For another country to replicate what Taiwan has in TSMC would be like a Manhattan Project. Intel is attempting it with a $32 billion investment in the US, but even with that, people are extremely skeptical that they will be able to close the gap. And the third company is ASML, based in the Netherlands. ASML is the only company on Earth that has commercialized the extreme ultraviolet technology required for cutting-edge chips. Nikon and Canon can't match it. So NVIDIA designs it, TSMC makes it, and ASML makes the machines that make it possible for TSMC to do so. That's the simplified supply chain for the most important technology of our era, running through essentially 3 companies. There is one other critical subcomponent that is frequently overlooked. High bandwidth memory, or HBM, has become a quiet bottleneck because a GPU's usefulness is tied to the memory that is feeding it. SK Hynix currently leads the market with more than 50% share. Micron and Samsung are chasing from behind. But demand has been so strong that supply has been fully matched by major contracts. HBM has already seen gains via optimization for AI, but many believe that there are a lot more gains to be had, and this could continue to improve the speed of the models and the economics for the model companies. Side tangent number 2, on compute. Software lock-in in the GPU space is a fascinating piece of this puzzle. During college, I consulted NVIDIA, and I learned a ton about their partner landscape. It made clear that the partners were not going to leave NVIDIA hardware anytime soon due to their software being optimized for NVIDIA GPUs. They were using the NVIDIA offering of CUDA. CUDA has essentially become the AI operating system. It's the industry standard, and it's why even if you built a competitive chip to NVIDIA's GPUs, customers might not switch because their entire code base is optimized for the NVIDIA ecosystem. Yet, most of the major players are trying to build their own chips. And why is that? 2 reasons. Cost and dependency. Google built TPUs, or tensor processing units, that were custom designed for their AI workloads. Because of their chips, Google has allowed themselves to be the lowest cost producer of tokens. A token is just a metric for a small piece of text or something that a model generates. Due to Google having their own TPUs, they've been able to keep prices artificially low for their in-house model Gemini. This sucks a lot of the economic oxygen out of the room for their competitors that are using NVIDIA GPUs like Anthropic and OpenAI. But Google's cost advantage seemingly has an expiration date. NVIDIA's next generation of GPUs were delayed in their implementation in data centers. The new power, cooling, and physics requirements made for major data center redesign, which allowed Google to have a temporary window where they were ahead of the pack via their TPUs. But as these NVIDIA optimized data centers continue to come online through the rest of this year and next year, the cost to produce tokens with NVIDIA hardware versus Google hardware will narrow dramatically. I'm a bit of a dove, but on that podcast I mentioned earlier, Gavin Baker uses some really interesting analogies to describe these different chips, which I think paints an effective picture. The current or kind of past NVIDIA chips that a lot of these models were running on was the Hopper chip. And they're like a World War II P-51 Mustang. Google's TPUs are F4 Phantoms, but Blackwell, NVIDIA's newest generation of chips that all these data centers are soon to be optimized for, and that Anthropic and OpenAI run on, is an F-35. It was late to the game, but it's coming. The other companies are still trying to follow the Google play, though, of having their own chips which their workloads can be optimized for. At billion query scale, a chip optimized for your specific workload, considered an ASIC, can be meaningfully cheaper and faster than a Blackwell on that narrow task, even if it loses everywhere else. AWS's Trainium is built specifically to improve the economics of training workloads, and Microsoft's Maya was designed to optimize inference across their own infrastructure. Having your own chip also provides a little more supply chain protection, but not a ton because heavy reliance on TSMC and ASML remains. The message is clear. Nobody wants to be fully reliant on NVIDIA, but their ecosystem has led to such a moat that it still has the leading AI players signed to them for several years. An important nuance, and I think it's probably been clear with how I've talked about chips, is that from the outside looking in, it doesn't really seem like chip optimization is a bottleneck. Moore's law seemingly continues as these chips become more and more optimized for AI workloads. And the delay in the data centers being able to fully use these chips are continually being ironed out. So the constraint is shifting. Rather than compute, energy and data are emerging as the harder ceilings to crack. So let's end this side tangent and get into data. While the first two building blocks of energy and compute ensure that AI can be cascaded across the economy and used at scale, I see data and algorithms as the most important components to these systems actually becoming more intelligent and not just more available and faster. So the energy powers the data centers, the chips sit inside the data centers, but what are the chips processing? Massive amounts of data. The first wave of AI training was essentially just a massive scrape of the internet. Models like GPT-3 and GPT-4 were trained on enormous crawls of web text, books, Wikipedia, Reddit, basically everything that humans have published online. But we're hitting a wall. We're running out of high-quality, human-generated data for the models to train on. So the data industry is seeing two key trends. One is synthetic data. This is AI-generated training data using existing models or simulators to expand the current training set. Gartner predicts that by 2026, 75% of businesses will use generative AI to create synthetic customer data. But the key nuance is that synthetic data scales human data. It does not replace it. It works best when it is paired with real human conversation, decisions, and feedback. The other trend we're seeing is depth over breadth. For years, the dominant strategy was, like I said earlier, scraping everything you could find, the breadth approach. But as that method continues to plateau, what benefits these models is going deep in specific domains. My Japanese friends tell me that GPT voice has an American accent when it speaks Japanese. My Japanese is still so terrible that I can't detect it, but ultimately this is a microcosm of there not being a lot of great raw audio data from different languages for these models to train on. Given the current model architecture, which I'll get more into in the algorithm sections of this video, it still learns very inefficiently. So the model companies will likely continue to compete to get deep domain-specific data while trying to parallel path and solve some of the algorithmic problems. For that data to make GPT voice speak in a better Japanese accent, it literally could mean trying to pay voice actors to speak in Japanese and recording that conversation and having effective labeling and indicating different emotional tones and the sort to allow the models to exercise a similar ability. The final layer, and probably the most interesting of this AI economy, is algorithms. The era of one model dominating every capability is seemingly over. Although all the companies are competing towards AGI, some are excelling in very specific domains, and the quote-unquote best model rotates every 3 to 6 months. Google is pushing multimodal reasoning. Anthropic is focused on coding and agentic tasks. OpenAI is balancing speed with general intelligence. DeepSeek is delivering frontier-level performance at a fraction of the cost, which has particularly appealed to startups and smaller companies. And Meta is democratizing access through open source. The most important algorithmic trend right now is called test time compute. This is the model ability to dynamically allocate more processing power to think harder on more difficult problems. This is one of the alternative solutions to just making bigger models. You make models that think more on the problems that warrant it. This is how reasoning models like OpenAI's O1 continued to have GPT innovating when NVIDIA's Blackwell chips were stalled. They squeezed more intelligence out of existing hardware and datasets. The other interesting trend is how fast open source models are catching up. Models like that from Meta and DeepSeek now beat GPT on many major benchmarks, which is huge. This means that frontier level AI is getting commoditized faster than we thought. Here's the most important side tangent, this one on algorithms. For the last 5 years, the mentality in improving these models was brute force and just make it bigger, scale it any way possible. More data, more compute, more parameters. That means more intelligence. That recipe kept on working to the surprise of many, but Ilya Sutskever, co-founder of OpenAI, believes that scaling era is ending. In some interviews late last year, he said a few things that I think should reframe how we think about the future of these models. His arguments are that we've hit the limit of what brute force pre-training can do. The models have been trained on all the useful internet text, but they still have this jagged quality to them. They can pass the bar exam and pass PhD level tasks, but still embarrassingly fail very simple tasks. He gives this example, which I think is very illustrative.
An example would be, let's say you use vibe coding to do something, and then you get a bug. And then you tell the model, can you please fix the bug?
Yeah.
And the model says, oh my God, you're so right, I have a bug, let me go fix that. And it introduces a second bug.
Yeah.
And then you tell it, you have this second bug.
Right.
And it tells you, oh my God, how could I have done it? You're so right again. And brings back the first bug.
Yeah.
And you can alternate between those.
Yeah.
Ilya compares the current model architecture and the possible other model architectures to two students, student A and student B. Student A practices for 10,000 hours, memorizes every concept, and wins the competition, but lacks deep understanding. Student B practices for 100 hours, but actually understands the concepts. Current models are student A. They've been optimized toward the benchmarks, but the ability to reliably apply knowledge to novel situations is still dramatically worse than what most humans can do, especially those specialized in the respective domain. So Ilya believes that we are ending the period of scaling and entering another era of research. And though Ilya may be the most well-regarded AI researcher alive, now spending his time since leaving OpenAI researching alternative algorithmic and architectural approaches, betting against scaling has historically been like betting against the Belichick-Brady Patriots. It kept working long after people said it shouldn't. OpenAI and Anthropic leadership remain publicly bullish that scaling data, reinforcement learning environments, and compute will resolve many of the current limitations. But it's hard to ignore the bottleneck in quality training data, the physical energy constraints on orders of magnitude scaling, and the fact that even at current scale, after consuming most of the internet and spending billions on compute, the models still fail in ways that suggest something fundamental is missing, not just something incremental. I think it is key to point out that still the current model skills have not cascaded across applications. And though we may need more algorithmic advancements for these systems to become radically more intelligent and actually cross the thresholds of true AGI or superintelligence, our economy is still likely to be fundamentally shifted, just as the current level of artificial intelligence is deployed in a variety of rote cognitive task domains, and likely in the background to potentially help them solve a lot of the data and the energy and the compute problems. These model companies will be parallel pathing these algorithmic problems to make their models potentially better resemble student B rather than student A. That's the AI economy. Energy at the bottom, algorithms at the top. And at every layer, there is a small number of companies and a whole lot of money shaping what's next. In the next video, I'm going to take this framework and use it to make predictions and recommendations for people playing in this economy. What this means for jobs, for investing, for SaaS, and for how you should be positioning yourself right now, especially for younger professionals. Subscribe so you don't miss it, and please comment any additions that you think are fascinating to the current AI economic landscape. And as always, smile at strangers and trust your curiosity. Thank you for watching.